I hope the recording starts. Okay, it started. All right. Good morning, friends. Sorry for the delay. Yeah, so let's begin. So quick recap of what we did in the last lecture. But before that, reminder. So we have a tutorial session in the evening today, 6:30 to 7:30, and next class will happen day after tomorrow, which is August 28th, Saturday, at the usual timing. Right. So that's a buffer day given to us, and we'll be utilizing that. Okay. So, okay, is there anything on chat already? Is everything okay now? Somebody is saying start creating another meet for whatever reason. Uh, one last confirmation. Is everything okay now? Am I audible
Yes,
and is
sir.
my screen visible? Good.
Yes,
Okay,
sir.
so let's
Yes,
continue.
sir.
Yes, sir.
Yes,
Cool.
sir.
Cool. So let's continue. All right. Yeah. So what did we do in the last class? We said how do we compare the cardinality of two sets? We said that the cardinality of set A is respectively at most equal to or at least the cardinality of set B if there exists respectively an injection from A to B, a bijection between A and B, and injection from B to A. Okay, so now if A itself is an empty set, then the first condition is same as saying there exists a surjection from B to A, and similarly if B is an empty set, the third condition is same as saying there exists a surjection from A to B. Okay, so now somebody we got a anonymous question on Piazza which asked that is it always true? So the question was as follows. So let me write it. So question: given arbitrary sets A and B, is it always the case that at least one of the following statement holds? Right. So, and what are the statements? There exists an injection from A to B, and the second statement is there exists an injection from B to A. Right. So the question is really asking, can we always compare the cardinalities of two sets, or could it be the case that, well, you have two sets, but there, I mean, you just can't compare the cardinalities of those two sets because there neither exists an injection from A to B, nor does there exist an injection from B to A. Okay, so I must admit this question never came to my mind so far. Okay, but and then I did a little bit of search, so it's not trivial to answer this. I agree, it's not so trivial, and I did a bit of search. Wikipedia said that okay, this is true. Okay, under the standard set of axioms we are working with, but the references it gave were to one paper and one book, and both of them were in German. Right, so that's where I got stuck. Okay, so secondly, I consulted the books. So Kenneth Rosen said that it is clear that this is true. I mean, it's not at all clear to me why this is true, frankly speaking. So I don't know why they said it's clear that this is true. And then the other book, this LLM book, said stated this thing as a fact without giving the proof. Right, so it appears to me that this is rather a deep statement, and we should not worry. Or what I'll do is I'll try to search whether there is a easy and understandable proof of this, written in English, of course, and then I'll share it with you. Right, so if either I don't find a proof written in English, or it's kind of too complicated, it kind of heavily relies on the very basic set theoretic axioms, then maybe I'll not share it with you. Then we'll just accept this as an axiom. Okay, so this is, so let's, for now let me just write it as so this is true but the proof is out of scope for us. Okay, so apparently there is something more happening on chats. Oh, nothing. Okay. Okay, so somebody has raised their hand. Aradhya, yes?
So I think this is called the axiom of choice.
It is not called the axiom of choice. The apparently, okay, from what I read, the proof relies on the axiom of choice. So I'm not sure whether this is kind of equivalent to the axiom of choice, if you have heard it. So the question is, okay, so from what I read, if you have the axiom of choice with you, then you can prove the statement. If you don't have axiom of choice, but you take this as an axiom, can you actually prove the axiom of choice? It's not, I don't know. Maybe it is the case. I'm not sure. So let me not comment on that. Yeah, right. So if you, Aradhya, if you find some more useful information, just share it with all of us. We'll love to read it. Okay.
Okay, sir.
Yeah, thanks. Okay, good. Yeah, so what else did we say? In the last class, we defined the notion of countable sets, and we said that a set is countable if its cardinality is at most the cardinality of the set of natural numbers, right? So how do you, what are some ways of proving a set is countable? So what we essentially did last time was that the claim the following statements are equivalent, right? So what does this mean? When I say that the following set of statements is equivalent, it means that either all of them are true or all of them are false. Okay, so okay, so I should say it this way. So let A be a set, then the following statements are equivalent. Let A be any set, the following statements are equivalent. What statements? So first, A is countable, right? Second, again, this is just the definition, follows from the definition. Yeah, so there exists an injection from A to the set of natural numbers. Third, A is not empty, or sorry, A is empty, A is empty, or there exists a surjection from N to A, right? What other conditions did we see yesterday? I mean, in the last class, right? What are other ways to prove that a set is countable? We also saw that, yeah, go on.
Injection from
Somebody
A
was saying,
to B is a countable.
sorry?
There exists an injection from A to B where B is a countable.
Ah, good. Yes. So there exists a countable set B and an injection from A to B. And what is the fifth condition now? Right? So what can I say in terms of surjection using the same idea?
There exists a countable set B and there exists a surjection from B to A.
And what about this A being empty? Right? So you'll have to worry about it. So what we can say is A is empty, or let me put it into parenthesis for disambiguation, right? So, or what? There exists a countable set B um, and a surjection from B to A. Okay, so we are just giving a set of tools for us to prove that some sets are countable, right? So we'll use whatever tool is convenient for us depending on what set we are trying to prove to be countable. Okay, so we also proved in the last class that some sets are countable, right? So we proved that the following are countable sets. What did we prove? We proved that the set of integers is countable, n cross n is countable, z cross z is countable, the set of rational numbers is countable. Did we prove anything else? Right, so we proved some kind of, yeah, go on.
No, sir. Rational is covered.
Rational is covered. Yeah, we also proved that if we also proved that this union A1, so for every n in the set of natural numbers, we proved that the union A1 union A2 union, right? So AN is countable if every AI is countable, and we also proved that this Cartesian product A1 cross A2 cross AN is countable if every AI is countable. Right, so we just did it for two sets. We really didn't do it for every n, right? But I'll leave this as an exercise for you to do by induction.
So
right?
we even did for a union of countable number of sets.
Sorry?
We even did for the union of a countable number of AIs.
We didn't exactly do it. We were yet to do the proof. We just stated the theorem, right? We didn't do the proof, no?
Okay, I think we may have discussed it.
Yeah. So we'll do the proof today. Let me just finish this off. Okay. Fine. So now our job, okay, so the theorem we stated last time was the following, right? So let A1, A2, A3 and so on be a countably infinite collection of sets, right? So what we are trying to prove is if you have a countable collection of sets and each of the sets is countable, then their union is also countable, right? So when you say a collection is countable, either it is finite, the collection is finite, the number of sets is finite, or the collection itself is countably infinite, right? So we covered the case of a finite collection over here, right? So let us worry just about the countable collection. Okay, so you have a countable collection of sets and each set in the collection itself is countable. Okay, so now we want to prove that the union of all these sets is also countable, right? So proof. Right, so what we'll do is right, so we'll use, yeah, so okay, first of all, let's do a bit of pre-processing. Okay, so if some AI is empty, we can just remove it from the collection. Okay, so without loss of generality, right, we may assume each AI is a non-empty set, right? So even if, yeah, so what you could do is if some AIs are empty sets, then you can just remove them from your collection. That is not going to, that is going to create a smaller collection. So it's still going to be a countable collection. Okay. And moreover, it is not going to change this union. Okay. So we may assume that, right. So this statement deserves a justification. It's just that it's so obvious that I have not written it. Okay. So now suppose each AI is non-empty, right? So therefore, clearly the union over I in N AI is non-empty. Okay, so what we'll do is we will construct, right? So this is a proof by construction. We'll construct a surjection from n cross n to this union. So yeah, so should we call it something? Okay, fine, let's leave it as it is. Union over I in n. Okay. Right, so what are we doing? We are using this fifth property, right? So we are showing that there exists a countable set B, namely n cross n for us. Abhinav, I'll come to your question. Yeah, and then we are showing that there exists a surjection from n cross n to your set A. So that way you will prove that A is countable. Abhinav, yes?
Sir, I have a doubt in this without loss of generality. And what is the
Okay.
criteria of writing it? Like, how do I know whether I need to prove something or just write without loss of generality?
Okay. Good. Okay. So usually when you write, you'll write it in two scenarios, right? Scenario one is where the proof is kind of obvious if your assumption is false, right? So what have we assumed over here? Each AI is not empty, right? So if your assumption is false, then the proof kind of reduces to the case where your assumption is true, right? So what are we saying over here? If some of your AIs are empty, just drop off those AIs, you'll get another collection that will still be either that will be a finite collection of sets, in which case you are done by the earlier proved claim. Otherwise, it will still remain countably infinite, and then you can use the claim for countably infinite collection when all the AIs are non-empty. Does that make sense?
Yeah, but like it's long statement. We need to prove it, right?
Sorry?
Sir, that there are cases if AI is not equal, some AIs are equal to 5, then this happens. So
Yeah.
shouldn't we write that instead of saying this?
Fine. Sounds very reasonable. Sounds very reasonable. Fair enough. So should we do that?
No, not here. I'm asking for the exams. Like in the exam, should we write that or not?
Acha. So it's safe to write it. Okay, it doesn't hurt, right? So what the danger is if you kind of don't use this without loss of generality notion in the correct manner. I mean, yeah. If you don't have good understanding of it, you might use it in an incorrect manner, and then what you assume without loss of generality is actually with a loss of generality, right? So that is the danger where you could step into, right? So unless you feel confident that the way you are using it is correct, just don't do it. Okay, it's safe
And
to
sir,
be yeah. Yes,
what was the
Abhinav?
scenario 2? Scenario 2?
Yeah. Scenario two is where the situation is kind of symmetric, right? So if you prove for one of the two cases, the other follows by symmetry,
That is fine.
right? So we have seen this earlier. We have seen
Yes,
this
yes.
in the friends and enemies case. Okay.
Yes.
Any more questions about this without loss of generality notion? Is there something on chat? Okay, nothing. Good. Okay, so this is a proof by construction, and then we are using this fifth statement. We are using the fact that the fifth statement implies the first statement over here. Okay, good. Right. So how do we construct? So what do we know? So since each AI is countable and non-empty, right? What do we use? So right, so each AI, we now use the fact that the first statement implies the third statement, right? So AI is countable, AI is not empty, so therefore there exists a surjection from n to AI. Okay, so since AI is countable and non-empty, there exists a surjection let's call it GI, going from AI to the set of natural numbers. Abhinav, do you have more questions? Your hand is up. Okay, cool. Right, so this happens for all I. Now let's define the surjection. So define, right? So our job is to construct a surjection from, oh, did I write it in the wrong way? So I should have written surjection from union of AIs to n cross n, no? Or other way. Sorry. Yeah, my bad. Sorry, there exists a surjection from n to AI. Yeah. Sorry for the confusion. N to AI. Okay. So now what? So yes, somebody saying something. Okay. Yeah. Is there anything on chat? No, chat. Okay. Okay, fine. So let's define the function from n cross n to this union over all AI, right? So define G going from n cross n to union over I in n AI as, right? So we define G of Mn to be the following, right? So what you are doing is you take the mth set, okay, right? So you take the mth function out of these, so you apply gm to the number n, right? So remember that this object is in the set am, and therefore which is a subset of the union over all I in n. Yeah. Right, so this function makes sense, right? It takes every element of the domain into some element of the codomain. Okay, so this is a legitimate function. So now why is this a surjection, right? So right, so for any, okay, so right, so we want to prove that this is a surjection, which means we want to show that for any element of this union over, okay, where is my pointer? Yeah, for any element of this set, we want to prove that it has a pre-image, at least one pre-image. It could have more. Okay, so consider any element any A in the union I and then AI, right? So because A is in the union, it means that, so therefore there exists some n in the set of, or maybe I should be consistent. I should say there exists some m in the set of natural numbers such that A is actually in AM. Right? This is just by the definition of the union of sets. Now, because A is in AM and GM is a surjection from N to A, right? So GM is a surjection from N to AM, right? So that is our assumption, right? So what does that mean? So therefore, there exists some N in the set of natural numbers such that GM applied to N is equal to A. Right? So this is exactly what we wanted to prove. So therefore G is a surjection. Right? So this is the end of the proof. So therefore union over I in capital N AI is countable. Is this okay? Any question? Let me pause for a few seconds. Okay, raise your hand if you, okay, there is a question apparently. Vivanshu?
Sir, it is not given that all AIs are disjoint sets, so small a can be more than one AI.
Sorry, AIs are what? Disjoint or not disjoint? What did you say?
Sir, AIs are not, AIs are disjoint. It is not given, so small a can be in more than one sets.
Correct. Correct.
Uh,
So in that case, it will have more than one pre-images, which is fine.
yes, sir. Okay.
Okay. We just want this function g to be a surjection, no?
Yes, sir. Yes, sir.
In fact, it could very well be the case that all these AIs are finite, and even the union of all of them, although the number of sets is infinite, their union is finite. Even that is possible. Okay, so in which case, some elements at least one element is going to have infinitely many pre-images. Fine. Okay, good.
So, like we did this proof in which we made a surjection from n cross n to A. Like the choice of making a surjection for this only, that like so that we would not have problem with A being in multiple sets, right? Otherwise, we were creating injections from A to n cross n.
Correct. So if you were to create an injection from union of AIs to n cross n, the first step which you would have probably done is from each AI, remove all elements which belong to the previous AJs and something like that, so that it becomes a disjoint union, and then you have a well-defined injection. But then I kind of avoided getting into all these complications by actually designing the surjection. Is that okay?
Yeah. Basically, yeah, to make our proof simple, right?
To make the proof simple. So you can take it as an exercise to show that there exists an injection from union of AIs to n cross n, or rather construct an injection the way we constructed a surjection. Okay, and that is also, so for the very same reason I used n cross n, I didn't use n. Okay. Yeah. All right. So now what? Now we saw that, okay, so just like the finite union of a collection of countable sets is countable, we also saw that a countable union of countable sets is also countable. What about the countable Cartesian product of countable sets? Okay, so that is what we will start looking at now, right? So if A1 through whatever, you have a countable collection of countable sets, you take their Cartesian product. What is it? Is it empty? Is it whatever? Countable, finite, uncountable? What is it? So we'll figure out. Okay. So in the first place, so the very basic question we want to answer is the following question: are there sets which are not countable? Okay, so otherwise, if no such set exists, then this notion of countability is completely useless, right? If every set is countable, what is the point in having this term, right? What is the point in having this definition added to your discrete math syllabus? Okay, so definitely there exist sets that are not countable, and I think some of you also found out on Wikipedia or whatever, some sources that that the power set of the set of natural numbers is not countable. Okay, so actually let's also, so there was some, somebody posted some incorrect proof of the fact of the statement that the power set of natural numbers is countable, but what it proved was that the set of finite subsets of natural numbers is countable. So let's maybe do that before we go on to uncountability. All right, so the claim we are making is, let S, or see the different symbol, F be the set of S subset of, let me just write it in plain English. Let F be the set of finite subsets of N, then F is countable. How do you prove this? Aradhya?
So I think that for proving uncountability of a set, we would require a base uncountable set with which we can have a injection or surjection. So for that, we
Okay.
would first of all need a base uncountable set. But sir, if we think properly, then we would realize that to find a base uncountable set, we would need to show that there does not we would our approach would be to show that there does not exist an injection from the given set
Hmm.
in question to natural numbers. So implicitly we would be only assuming that we would be actually assuming that two sets can be always be compared by sizes, because we are saying that if there does not exist an injection from our base set to natural numbers, then that set is larger than natural numbers.
Okay, okay. So couple of comments, we accepted that as an axiom anyway, right? Secondly, that is not exactly the way we'll prove something uncountable. We'll come to that. So for now, my question is the following: how do you prove that the set of finite subsets of n is countable? Can we use this earlier? Can you use this claim and prove that the set of finite subsets of n is countable? Hello. Yeah. Let's assume that f be a set, and we will define a function from f to n. F to n, fine, you can do that, but my question is the following: when you have this big hammer with you, why don't you want to use it? Okay. Right? Can you just write this f as a countable union of countable sets? Yes, we will take an element a1, a2 of f set. Suppose f contain a1 to an. Because it is finite, so we can say that n is finite, n is not infinity. No, wait. F is the set of finite subsets of n. F itself is not a finite set. Okay. Sorry. Right? So F is the set of all possible finite subsets of n. F is not a finite set. Divyanshu?
Yeah, like we can group them according to some basis in some sense. Like I think so. Like on the basis of this, something like that.
Okay, wait. So let's do this. So let's do a little bit of rough work over here. Let's do a little bit of rough work over here, and then we'll write down the formal proof. So what we are trying to do is write f as a countable union I in natural numbers of some fi's, right? So where each fi is clearly countable. How do you do this?
Sir, we can.
Hello? Yeah.
So we want to by something that, sir, if f is the set of finite subsets of n, so that means that there exists n naught such that the length of all the subsets is less than n naught.
I don't agree.
Sir, we can order the subsets according to the cardinality in the F.
That sounds good. Then you'll have to prove that the set of all subsets of size 100 is countable. That still requires a proof, no?
Yes, sir. Yes.
Yeah. One sec. So somebody said that okay, there must exist some n naught such that every set is a subset of the first n naught. Is it clear to everyone why that is not true?
So that
okay, Arin?
I think that would be what Dhruv is saying.
Sorry?
Sir, I think what Dhruv is saying would be true, that there exists some n naught such that.
Okay, what is the claim? There exists some n naught such that?
Such that each fi is a subset of.
No, but you haven't defined FIs. What is your definition of FI?
Each element of f. Okay. Each element of f is a subset of natural numbers ranging from 1 to n naught.
Is a subset of 1 through n naught. Is that the claim?
Yes, sir. So anyways, I was not saying this. I was saying something else. I was defining fi.
Okay. Yeah, one sec. So, Arin, 1 sec. So let us convince ourselves that this claim is not true.
Okay, sir.
Right. So, well, so if you look at F, right, so you have all these sets in F, right? So the singleton 1, singleton 2, singleton 3, right? So all these sets are in F, right? So therefore this claim is not true. There exists a number n naught such that every set in F is a subset of 1 through n naught.
I was saying that every set in F, every element of F has its size less than equal to n naught.
So for every element of F, there exists an n naught such that it is a subset of 1 through n naught. Is that what you are trying to say?
No, sir. The F is a set of subsets. So
Correct.
if you take a subset, then its size will be less than n naught. I am asking.
Okay, so you're talking about the size. I'm talking about the maximum element. Yeah. So we are essentially using the same idea, right? So it's just a switch of quantifiers which is making the statement false, right? So what we are saying is, so okay. So let me just clarify this. Yes, yes, there were some hands raised. I'll come to them. Just give me a moment. Yeah. So what we are saying is, if you say that there exists some n naught such that for all s in F, S is a subset of 1 through n naught, this is false. But instead of that, if you say for all S in F, there exists some n naught, right? Which means that this choice of n naught really depends on the set you're talking about, such that S is a subset of 1 through n naught. So this is true.
No, sir. The size of S is less than n naught. Like.
All right, fine. Size of S is less than or equal to n naught. Even this is true. Right?
So then with the mapping of natural numbers crossed n times, like n cross s n naught times, and use that.
Yeah. Good. Yes, that makes sense. So the argument is so maybe what I'll suggest is maybe you can write it as a formal proof and post it on the discussion forum. Okay, so just as a proof writing exercise. Yeah, that is another way, another idea, perfectly valid idea. Okay, Arin, did you have anything more to say?
Yes, sir. I was defining FIs. Sir, we can define FIs.
What's your definition of FIs?
Sir,
yes.
Since F is a set of finite subsets of n, then each F would have a cardinality, certain cardinality. Yes.
Correct.
So we can order the sets based on the cardinality, and when the cardinality is same, we can compare the least element of a set. By well ordering principle, there should exist a least element.
Okay. So what? Then what? So you are trying to construct explicit injection from this F to set of natural numbers?
No, sir. I'm trying to construct countable sets FIs such that their union is F, and then we can say
I see. So what is the definition of FI now? What is your definition of FI?
So FI is a subset of natural number. FI is a finite subset of natural numbers, and FI is the
first of all. Wait. So FI is supposed to be a collection of subsets of natural numbers.
Okay, so sorry.
Okay. Aval?
Sir, why is it true that every subset will have a size less than equal to n naught for some n naught?
So it's a matter of this quantification, right? So for every set, there exists some n naught such that the size is at most n naught.
Okay, for every set. Okay, right. I thought one n naught for all the sets.
Every set, there exists a choice of n naught which is dependent on the set.
Okay.
Right, such that something happens. That's why it is true. Manthan?
So we can place every element. Suppose the first set of the F set will be a subset from the n, right? So we can place it in the first number line x. Then we can like that we can do place in the xy plane.
What is the plan? Wait. So if you are proving something as countable, which part of this are you using? Are you trying to show 2, 3, or 4, or 5? What are you doing?
N cross n. Injection from n cross n.
Injection from n cross n. Okay. How do you do that? Injection from n cross n. That's not good enough. Injection to n cross n is.
Sorry, 2.
So what is 2 now?
Injection from F to n cross n.
F to n cross n. Okay. How do you do that?
We will draw an xy plane, positive x and positive y, and in the x-axis we place the elements of the Fi set. And such that
so you place the elements of Fi. Then what?
Phi, and in the y-axis our I will be there. I.
Okay.
Only I.
Fine. And then what?
Suppose I equals to 1, then we will place the element of Fi. Then we can show that easily that the F. I mean, it's a countable set, right? Because
Manthan, hold on, Manthan, one sec. So I'm not sure whether your idea is going anywhere. So I would rather suggest you to think on it, come up with a proof, and then discuss, share it on the discussion forum.
Okay, sir.
Is that okay? Right. So just give it a serious thought. Just understand what you want to prove, and then let us know what is happening. Ishan.
Yes, sir. We can take Fi to be n to the power I, which is n multiplied by I times, and then for any general n to the power I, we can use that the prime number proof which was discussed.
Wait. What? If Fi is what?
Sir, the natural number set of natural numbers multiplied I times.
Set of natural numbers multiplied I times. Acha. This one.
Yes, sir. And
I times. Okay.
To prove this, we can take any I prime numbers. We can take the first I prime numbers.
No, first of all, no. Hold on. So if you are trying to write F as a union of these Fi's, Fi must contain subsets of natural numbers. Subsets of n. And now if you define Fi to be this, if Fi doesn't contain subsets of n.
It is the sir, it
again. So just give it a thought. You might have the right idea. Put it in the right words. Give it a thought and put it in the right words and share it with us. I'm sure you have the right idea. Is it okay, Ishan? Just take your time. Okay, Aradhya, your hand is up.
Sir, I do not agree with the claim that for all S belonging to F, there exists a n naught such that mod S is cardinality of S is less than or equal to n naught. Like I can construct an F where there does not exist such an n naught.
No, so just understand the order of quantification, right? So you're saying that for every finite subset of n, there exists some natural number n, which means this natural number could depend on what subset you have chosen. Right? So understand the difference between this statement and this statement.
Okay, yeah, right.
Okay, yeah, fine. Okay, Sachit, one last question before we go ahead.
So
Sachit?
That we have decided on the right hand side, like the one that Dhruv said, mod S.
Sorry?
Like Dhruv said regarding the mapping for mod S. Like I am what was the mapping?
No, I don't think he. He's going to write apparently. He's going to write and share with us.
Okay.
Okay. Manthan, what is it?
Sir, if we can prove that for every subset there exists an n naught, different n naught, it depends on the subset, then we can also say there exists only one n naught which satisfy all the subset.
No,
we can take the maximum of all that n naught.
Manthan, you're saying if everybody in your class has a girlfriend, then there exists a girl who is the girlfriend of everybody in your class, right?
No, but that's different, right? Suppose the value of n naught for every set is 1, 2, 3 ... like something like that, random values.
Yeah.
Then we can take the maximum of all that random values and define that every subset size is less than this value.
Like there are infinite subsets, no? So you cannot do maximum on infinite.
Exactly. So Manthan, let's take this to a discussion forum. Okay. Fine. Okay. Let's come back, class. Enough discussion on this. So the idea is to express F as a countable union of countable sets, and the way I'll do it, there could be other ways of doing it, perfectly reasonable ways. So okay. So define Fi to be the set of all S subset of n such that for all m in S, m is strictly less than I. Right? So all I'm saying is that the maximum element of S must be strictly less than I. Right? So every finite subset has a maximum element, right? So therefore every finite subset is going to belong to some Fi. Right? So therefore F is the union over I in capital N of Fi's. Right? So this is a countable union. Now what is, so observe, but each set, okay, what is Fi after all? Fi is nothing but Fi, right? So set belongs to Fi if and only if it is a subset of the set 1 through I minus 1. Right? So Fi is just the power set of the set 1 through I minus 1. Right? So therefore Fi is finite. Right? So thus F is,
why does Fi have to be the power set? It's not necessary that
right?
capital F had all finite subsets.
Look at the definition of Fi. Fi is the set of all subsets of N, whose maximum element is less than I.
Okay, so I have a doubt in the definition of capital F. So does capital F have to include all the finite subsets of N?
That is the, by definition, be the set of finite subsets of N. That's the way we have defined F. Okay, we have not said that, we have not just said that, okay, every element of F is a finite subset of N. That's not what we have said. We have said that F is the set of finite subsets of N. Okay.
So it means that it contains all the finite subsets, right?
Exactly. Yes. Okay. Yes. All the finite subsets and nothing else.
Yeah. Okay.
Okay. So thus F is a countable union of countable sets. Right. So therefore F is countable. Okay, any more question as far as this proof is concerned? Aradhya, yes.
So I think we can just extend the principle of the fundamental theorem of arithmetic. Like we can say that we can define the function by saying that we take the product of the ith prime number.
Aradhya, one second. Are you trying to construct some kind of injection / surjection from F to something?
Yeah.
Okay, let's go to the discussion. Okay, so that it remains in front of everybody's eyes. No? So you might have the right idea. Just post it, share it. Is it okay, Aradhya?
Yeah.
Okay, cool. Let's see. Okay, fine. So F is the collection of finite subsets of N, then F is countable. But what about the collection of all subsets of N? Right? And somebody correctly figured out that that is in fact uncountable. So let's do that. So theorem. Right. So the claim is that 2 to the power the set of natural numbers is an uncountable set. Manthan? Manthan, your hand is up. Yeah.
Sorry, sir.
Okay. Fine. Okay. So our plan is to prove by contradiction. So proof by contradiction. Right. So suppose, so what do you assume? You assume the opposite of what you are trying to prove. So suppose 2 to the set of natural numbers is countable. Right. So clearly, I mean, we know 2 to the size of 2 to the set of natural numbers is non-empty. Right. So therefore, there exists some surjection G going from the set of natural numbers to its power set. Okay. So let us pause and let us do some. Let us just see the intuitive idea behind this proof. Okay, so we'll come back to this proof, but let us see the intuitive idea. So let us create this as some kind of a table over here. Okay, so on. Okay, so I'll have a row for every natural number. So this is an infinite, I mean, countably infinite table in both directions. I'll have a row for every natural number 1, 2, 3, 4, 5, and so on. And I'll have a column, right? So I'll have a column for every subset of natural numbers, right? So we know that G going from n to 2 to the power n is a surjection. That's what we assumed, right? So if we use G of 1, G of 2, G of 3, right? If we create these kind of columns, every subset is going to get a column. Okay. Now let us note down these subsets, right? So let us put a tick mark, right? So look at G1. It could be a finite set, infinite set, I don't know. But let us put a tick mark corresponding to all elements that G1 contains. So probably G1 contains this, doesn't contain this, contains this, no, something, right? So in general, in the ith row, right? So in the ith row and the gjth column, I'll put a tick mark if the number I belongs to G of j, and I'll put a cross otherwise. Right, so this is the table that I'm trying to create. Right, so this is just a thought experiment. I'm not writing the proof for now. Okay, so now we somehow want to get a contradiction. Okay, so how do we get a contradiction? We'll get a contradiction by proving that, okay, G is actually not a surjection. Right, so the image of G is going to miss some subset of natural numbers. Right, so idea, get a contradiction by constructing a set S, which is a subset of natural numbers, which is not in the image of G. That is, there does not exist an I such that G of I is equal to S. Right, so this kind of set, if we construct, then we are done. Okay, so how do we construct this set? So let us kind of do it one step at a time. Right, so we want what do we want? So we want S to be different from G1. Right, so in fact we want S to be different from every GI. So how do we make S different from G1? We'll look at this entry. Right, so G1 does not contain 1. So we'll include 1 in S. Okay, so let us take an example and fill up this table somehow. And let us also take G4 maybe. Right, so if we look at this table, right, so G1 does not contain the element 1, so we'll put 1 into S. Right, so G1 does not, 1 is not in G or G of 1, so therefore include 1 in S. And as soon as we have one element where S and G1 don't agree, that implies that S and G1 are different sets. Okay. Similarly, we want S to be not equal to G2, right? So what you'll do is the same idea, right? So we'll look, G2 contains the element 2. 2 is in G2, so therefore not include 2 in S. This will ensure that S is different from G2. Okay. Similarly, 3 is not in G3, so you will include 3 in the set S. And similarly, 4 is not in G4, so you'll include 4 in S, and so on. right? So this will ensure, right? So this ensures that for all I, S and Gi don't agree on membership of I. What do you mean by that? So it means that exactly one of them contains the element I and the other guy does not contain element I. Okay, so therefore this implies that S is not equal to Gi for all I. Okay, there is something on chat. Ishan says it may be that AI are finite. Oh no, but that's an old comment apparently. So that doesn't apply over here. Okay, Divyansh.
So like, I know that this is like widely accepted, this Cantor's diagnostic argument, but like it's not intuitively that like acceptable. Like I don't like, for example, had like here we are dealing with infinities. Okay, we are saying that ith element exists, but like had it been finite, then we would only have like n GIs, whereas the rows would have gone to like 2 to the n. So like it's intuitively.
No, wait, I don't understand. I don't understand. Hold on. So what are you trying to prove firstly?
But I'm not trying to prove. I'm just saying that it's intuitively, like we are saying we can always find an ith set. Like at position I, we are just looking at GI and just that changing it. But like like this the number of GIs is much smaller than like kind of, because in a finite case, when we have it would be like 2 to the n when it's finite, not n but a finite set, just any.
So you're looking at the power set of a finite set, okay, and then what?
But like so like this doesn't hold because like the n elements get exhausted before the 2 to the n, so like there exists one. But like we are just increasing it to infinity now. Like if like intuitively it is a bit hard for me to understand ki okay this should work, because like it's infinities, but like can you like intuitively, do you have any
so the idea is still the same. Idea is still the same. So the idea is same as yeah. So how do I tell it? So yeah, so it's kind of analogous to the finite case, right? So even in the finite case, you know that the size of the power set is strictly more than the size of the set, right?
Yeah.
Right. So here, that's what we are seeing. So these numbers, the integers, are not sufficient to index the power set of integers. That's all we are seeing. Except that this has now become an infinite set.
So I think he's confusing. He's thinking that one of the rows is of the order of natural numbers, and one of the rows, one of the axis is of the order of natural numbers, and the other axis is of the order of the power.
No. So both axes are countable. Both axes are countable.
Yeah.
And that, why did we do this? Because we started.
Because we are taking a contradiction.
Power set is countable.
Makes sense.
Okay, good. Divyanshu. Divyanshu, your hand is up.
Yeah. So like I'm also a bit confused in this. Like, anyways, whatever S we create, so it could be a subset of n, right?
Yes.
So isn't this kind of like a paradox? At the first place, we had that like G is a function from n to every subset of.
Exactly. So it is a paradox. And why did this paradox arise? Right. So why did this nonsensical situation arise? Because our assumption was wrong, and that is what is expected to happen in every proof by contradiction.
No, sir. Like it doesn't seem like a contradiction. It seems like a paradox. Like in the sense that it doesn't still say that G didn't have that element S.
So basically, what is a paradox? Paradox is effectively a statement which kind of, if you assume it is to be true, assume it is true, then it implies that the statement is false and vice versa, right?
Yeah.
Yeah. So paradox is a kind of a nonsensical statement, right? So which you can't assume assign a true or false value.
Yeah, like we can't assign it true or false. It's like we say
Exactly.
that it would be a false. Something
exactly.
Like that.
So what you have technically, what you have over here is you have this assumption that G is a surjection, right? So this is the assumption, and then that implies, so it's just one way. Okay, so G is a surjection, and that implies G is not a surjection, right? So it's not really a paradox. If you assume that G is not a surjection, you are not getting into paradox. You cannot say that okay, that implies G is a surjection or something like that.
Yeah. Okay. And
okay, so it's a one-way thing.
Anyway, S has to contain all the natural numbers, right?
S has to contain what? S has to contain all the natural numbers. Why no?
Like suppose if I take a subset of n, which is like n minus the element 3. So S would have to contain 3, right?
No. It depends on where that set appears in where that set appears as a column over here.
Okay.
Divyanshu, is that your hand is up?
Yeah, I'll lower it.
Acha, okay, fine. Okay, fine. Right. Okay, so right. So there exists a surjection G going from n to 2 to the power n. So now what? So now consider the set. Consider the set. S is the set of all what? Right. So it is the set of all numbers I such that I is not in Gi. Right. So this is the way we constructed S. Set of all I in the set of natural numbers such that I is not in G of I. Okay. So right. So now what? So now we want to claim that this S is not in the image of G, right? So let's do it this way. So G is a surjection. So since G is a surjection, G is a surjection. Yeah, G is a surjection. There exists some n such that there exists some n in the set of natural numbers such that G of n, G of n is in S. Okay. Right, and now here you really have a paradox.
Sir, why did we say belongs to S? You should say equal to S, right?
Sorry, my bad. G of n is equal to S. Sorry, extremely sorry. Yeah, G of n is equal to S. There exists some natural number n such that G of n is equal to S. And now the question is does n belong to S? Okay. So what do we have? So if n belongs to S, then what? Right. So therefore n belongs to Gn, right? But by definition of S, n should not belong to S. And similarly, if n belongs to S, n does not belong to S, what do you get? If n does not belong to S, then n does not belong to G of n. But again, by definition of S, what do you get? N must belong to S. Yeah, Divyanshu?
So you said that like I put up a set n minus 3, like it's a set of a subset which doesn't have 3. So some Gi would be equal to that. So anyway, so basically we'll exclude the element, right? Like we'll exclude
Right. So
Gi
you ask the
I.
question. See, you ask the following question. Some Gi is equal to your set, all natural numbers except 3. Is that I equal to 3? If that I is not equal to 3, then Gi contains I. So then I will not be in your set.
Okay.
Yes.
Yeah. Now,
okay.
Thank you.
And if that I turns out to be equal to 3, then you'll include 3 into your set.
Yeah. Okay, sir.
Okay, good. Okay, right? So therefore, yeah. So this, right? So this is a contradiction. Right? So n belonging to S and n not belonging to S, and similarly n not belonging to S and n belonging to S. So that is a contradiction, right? So therefore, right? So why did we get into this contradiction? We got into the contradiction because we assume that 2 to the power n is countable. So therefore, 2 to the power n is not countable, or in other words, uncountable. Okay. Yeah, Shibashish?
So here will we have to handle the base case that S is 5?
Handle the base case that what?
If S is 5.
S is empty. Doesn't matter, no? First of all, we are not giving a proof by induction. So even if S is empty, I can apply the same argument. Exactly the same argument.
So means that like if S is empty, then how can we tell that Gn and all those statements we can?
So S is empty, so G is supposed to be a surjection, right? So therefore, there still exists some n such that G of n is equal to the empty set, right? Now, yes. N, obviously, that n does not belong to S, but then by definition of S, that n should actually belong to S. So that is still a contradiction.
Yes, sir.
Okay. Yeah, cool. All right. So now, let me also mention a theorem which I leave for you to figure out as a part of tutorials. So theorem, right? So let A be any set. Any set. It could be finite, countably infinite, uncountable, whatever. I don't care. Oh, okay. So Viraj, you have a question? Your hand is up.
Sir, sorry if I'm missing something very obvious. I didn't really get if n does not belong to S, then by definition of S, n belongs to S. What am I missing? I'm not.
So if n does not belong to S, because S is equal to G of n does not belong to G of n.
Yeah.
Okay. So now look at this definition. Look at the definition of S. S contains all those integers I who don't belong to corresponding.
Yeah. Got it.
Okay. Thanks. Good. Yeah. So now, yeah. So this is one result that I'm going to leave for you to figure out as a part of tutorials, right? So let A be any set, absolutely any set. There does not exist a surjection from A to the power set of A. Okay, so what we proved a very specific case of this theorem where A is the set of natural numbers. Now we are claiming that let A be any set, you just cannot get a surjection from A to its power set. Okay, so this I'll leave. The idea is still the same. It's just a matter of writing it into a concrete readable proof. Okay, so this.
So for finite cases, can we change it directly by number of elements?
Sure, finite case, yes, agreed.
Okay, sir.
Okay, but then when you actually write down the proof for the infinite case, you will actually see that it even holds in the finite case. So you don't have to handle the finite case separately.
Okay.
Okay.
Yes.
All right. Cool. So what else did I want to discuss for this class? So now let us come back to this question. Let us come back to the question where you had this. Okay. Yeah. So question. Let A1, A2, and so on. So you have a countably infinite collection. B all countable sets. Right, so you have a countably infinite collection of countable sets, right? So is A1 cross A2 cross blah 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 cross, yeah, so this infinite Cartesian product necessarily countable. In very specific cases, it can be countable, right? So let's just consider the trivial case where the size of each AI is, let's consider the trivial case where one of the AIs is empty. Then the Cartesian product is empty, so therefore it is countable. If each of the AIs has just one element, then the Cartesian product is going to have just one element and it's going to be countable. Okay, but is it always countable? Any ideas? Okay, raise your hand if you think that the answer is yes.
Sir, like I had a small doubt. Whenever we write something like A1, A2, dot, 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 it means this is an uncountable infinite collection, right?
Correct.
Yeah. Okay.
Correct. Yeah. Okay, raise your hand if you think the answer is yes. Okay, raise your hand if you think the answer is no. Oh, Arun, you think the answer is yes or no? What is it?
Sir, I think the answer is yes, but I cannot
Yes.
get to a proof.
Okay, Arun thinks that the answer is yes, fine. So now I hope everybody who has raised their hand right now thinks that the answer is no. Okay, so Rishabh, do you want to tell what idea you have in your mind? Why do you think the answer is no?
So you could think of it as like EI be EI be like the set 0, 1.
Okay, good. So for all
the I's.
All the I's. So what Rishabh is saying is A1 equal to A2 equal to, so all of these are just the set 0, 1, finite set. Okay.
Then their product will be sequence of zeros and ones.
Correct. Infinite strings of zeros and ones.
Yeah.
Yes.
And you could like easily map this string to the set to all subsets.
Very good.
N.
Awesome, Rishabh. Yes, you're absolutely right. Right. So observe that. So if all these AIs are 0, 1, then A1 cross A2 cross. So this infinite product is in bijective correspondence, is in 1-to-1 correspondence. So, or rather, I should say, then there is a bijection, from A1 cross A2 cross blah 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 to the power set of natural numbers. Okay, and what is the bijection? So you have, if you have, right, so where, right, so if you have this infinite bit string A1, A2, and so on, right, so this goes to the set of all I such that AI is equal to 1, something like this. Okay, so now obviously because this is uncountable, so therefore this is also uncountable. Right, so therefore in this case A1 cross A2 cross blah 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 is uncountable already. I mean, even if all the AIs are finite, you have actually constructed a case where the Cartesian product is uncountable. Okay, Ramanuj?
Yes, sir. I think you can like also have a bijection which is very similar from this to real numbers. If you just take, for example, AI is equals to 0 to 9.
Hold on. Yes, you can, but we haven't even talked about real numbers for now. Right? We haven't even established that. Oh, are you trying to say that the set of real numbers is what, uncountable or something?
Yeah.
Oh,
So set of real numbers is uncountable because this is uncountable.
Awesome. Yes, very nice. Yeah. So claim, let's do it immediately. The claim R is uncountable. Right. So proof what? Right. So we'll give a what? We'll give an injection. Construct an injection from this set A1 cross A2. Yeah. So A1 cross A2 cross blah blah blah, where, or rather, yeah, okay, fine. So where each AI is 0, 1 to R, right? And then the argument is what? What is the injection? Ramanuj, what is the injection?
So it was AI is equals to 0 to 9 when you can take that
Why do you need all that? Why do you need all that? Suppose you just have 0, 1. Well, how do you construct an injection?
So we can construct a binary number.
Exactly. Binary, wait, okay, binary is a bit tricky, but decimal certainly we can construct,
Yeah.
right? So this will go to the decimal number 0.A1, A2, A3. Okay, this is an injection, right? So this is in decimal. Okay, Ramanuj, I'll come to you, but somebody mentioned binary, right? So if I say that A1, A2 and so on, this infinite sequence goes to the binary number 0.A1, A2, A3, right, and so on. So if this is binary, so I claim that this is not an injection. Why? Right, if we interpret the number as a decimal number, then it is an injection, but if we interpret it as a binary number, it's not an injection. Divyansh?
So like it's similar to what happens that in decimal in 0.999 and
Perfect.
1 are the same. So it's something similar here.
Perfect. Very nice. Yeah, good. Right. So right. So the question is, what will the sequence 1 0 0 0 0 0 all zeros? What will this go to? It will go to the binary number 0.1, which is equal to half. And what will this go to? 0 1 1 1 1 1 1 1 1. Right. So this will go to something like 1 by 4 plus 1 by 8 plus 1 by 16 plus blah blah blah, which is equal to half. Okay, so this is an injection, but this is not an injection. So therefore, yeah. Anyway, but so that this implies that R is uncountable in any case. Right.
Sir,
so
I couldn't understand the idea and the question that you written, the previous one. Could you repeat it?
Yeah, one sec.
Yeah.
What question are you talking about? This question?
Yes, sir. So after you said that there is bijection from this to 2 to power n because 2 to power n is uncountable. After that step.
Oh, because 2 to the power n is uncountable and you have a bijection from some set to 2 to the power n, so then the cardinality of those two sets is the same.
Right.
So therefore the other set is also uncountable. Right. So if you want to concrete argument, so you have a bijection. Let me draw a diagram over here. Right. So you have a bijection between 2 to the power n and your set A1 cross A2 cross blah blah. Right. So you have a nice bijection over here. Right. So bijection means in particular it is also an injection.
Yes, sir.
Now if you had an injection from this set to the set of natural numbers, then by composing you will get an injection from 2 to the n to n. Right. So therefore this kind of injection cannot exist.
Acha. Okay, sir. And the notation that you've written there that it goes to I such that AI equals to 1.
Oh, acha. Yeah. So what I meant to say is I didn't give the bijection a name. So if I call this bijection as H, then what I meant is where H of this infinite sequence is equal to the set of all I such that AI is equal to 1. Is this okay now?
Yes, sir. It works.
Okay. Prabal?
Sir, I wanted to ask that in this decimal part, sir, if we take AI as 0 to 9, we will run into the same problem as in binary,
Exactly.
right?
Absolutely. Yes, you're right. Okay, fine. Divyanshu, any more question?
Yes, it's the same thing that Prabal raised. Like if we have this A1 is 1 and all others are 0, and then we have another thing that A1 is 0 and A2, A3 all others are 9. So won't they both map to the same number?
Exactly. So you will land up in the same problem if you take AI, if each AI to be the set of all 10 digits 0 to 9, and you interpret the number as a decimal number. you are going to land up in the same problem.
So then how
Okay,
is it
good.
an injection?
Oh, how is it an injection, right? So if two numbers differ, then they must differ in some decimal place, no? Right?
Can you repeat that statement?
Yeah, so if two real numbers R1 and R2 are not equal, if R1 is not equal to R2, so then there exists some decimal place where R1 and R2 differ, no? Right?
Yes, sir.
Yeah, so then therefore if you take the corresponding sequence, the sequence is going to differ somewhere. Okay?
But like then still we would say that they're mapping to the same number. Still we are saying it's an injection.
No. So acha. Oh, so you are saying that two sequences map to the same number. Acha. But that's why we are taking them to be decimal, no? Right? So if okay, so in decimal in decimal, a rational number with a finite number of decimal places can have another form where you kind of decrement the last decimal place and then append infinitely many nines, right? But those are the only numbers which have this weird behavior, right? So these numbers, the numbers in the image of this function, are not going to have that weird behavior. Okay.
Okay. So like yeah, then similarly we could have done for binary also.
Binary, that's still a problem, no? So if you are using all the possible digits or bits or whatever, then you are going to land up in the problem.
Like my main issue is that how can this cause a problem just by changing the number system, right? Like I don't think so we should ever land in a problem that where one number system holds and the other doesn't.
So basically the cause of the problem is the following. So basically consider any number system, let's say base whatever. Let me add a page. So let us say you have a number system where your alphabet is 1 through whatever b minus 1, sorry, 0 through b minus 1 and base b number system. And now if you have a number of the form let's say something dot something and then followed by infinitely many zeros, right? So you have some symbol over here. So this number is also going to be equal to this point, everything, and then you have a d minus 1 and then you have infinitely many b minus 1s, right?
Yeah.
So now if you okay, guys, could we take this to the next class because the time is up, or it's better if we discuss this on the discussion forum, right? Because that is anyway a digression from the main topic. Okay, fine. All right. So chalo. So we'll meet on in the evening today for the tutorial session, and the next class is on Saturday, 9:30. Chalo. So see you then. Lecture khatam.